Hi everyone, my name is David and together with my colleague Sepideh, we are going to present our project, combining big data, AI and 3D visualization for data center optimization. This project comes from the need to create a system that allows us to control the state of the supercomputer. Moreover, we can use the data to predict errors. We need to manage a lot of information about each node of the supercomputer. But first of all, let's take a look at the Marconi 100 architecture. Marconi 100 is made up of 55 racks. Each rack has 20 nodes inside it, and each node is composed of two 16-core processors and 4 GPUs. It is worth noting that with its 32 petaflops, it is one of the most powerful supercomputers in Europe. The data is found in the Examon database. We are going to extract and use only the ones we are most interested in for knowing the status of the nodes. These are temperatures, the power, and the status that tells us if the node is working properly. Once we have the data saved in files, I've created a Python application to visualize them in a simple way, using pandas to manage the information and the BTK library to display all the data in a virtual replica of Marconi 100. Now, I will explain how to go from data to 3D visualization using BTK. This library offers different classes that are responsible for carrying out different parts of the process. In short, they are divided into the following. Sources, used to read raw data. Filters can then be used to modify, transform, and simplify that data. Mappers are responsible for creating tangible objects with the data. And at the end of this pipeline, we can find the actors, which are responsible for encapsulating these objects in a common interface that has many freely modifiable properties. We are now seeing how this virtual replica has worked out. Each node has the following information: a text with the power it is using, a square representing the status of the node, green if everything is working properly, and red otherwise. In addition, on the left side of each node, we can see a heat map with all the temperatures of the cores of the node. And this is all about visualization.
Hi, my name is Sepideh. My task in the summer of HPC project in Chinica was detecting anomaly in dataset by using machine learning approaches. Anomalies, often referred to as outliers, abnormalities, or rare events, are data points or patterns in data that do not conform to a notion of normal behavior. Anomaly detection then is the task of finding those patterns. Here we used Autoencoder for anomaly detection. Autoencoders are neural networks designed to learn a low-dimensional representation given some input data. They consist of two components: an encoder that learns to map input data to a low-dimensional representations, termed the bottleneck, and a decoder that learns to map this low-dimensional representation back to the original input data. The model is trained by minimizing the reconstruction error, which is the difference mean squared error between the original input and the reconstructed output produced by the decoder. Applying an autoencoder for anomaly detection follows the general principle of first modeling normal behavior and subsequently generating an anomaly score for each new data sample. To model normal behavior, we follow a semi-supervised approach where we train the autoencoder on normal data samples. This way, the model learns a mapping function that successfully reconstructs normal data samples with a very small reconstruction error. This behavior is replicated at test time, where the reconstruction error is small for normal data samples and large for abnormal data samples. To identify anomalies, we use the reconstructions error score as an anomaly score and flag samples with reconstruction errors above a given threshold. As you can see, for encoder and latent layer, we used LSTM layer, and for decoder, we used dense layer. For training our model, we had some challenges. First, we needed to split time series dataset to train and test. In the case of time series, the cross-validation is not trivial. We cannot choose random samples and assign them to either the test set or the train set because it makes no sense to use the values from the future to forecast values in the past. Second challenges was evaluating the performance of our model. We had some labels with respect Nagios service that we wasn't sure we can use them as relative label or not. The more details about our approach is in the final report. Thank you for your attention.